Potassium phosphates are a family of chemical compounds that consist of potassium ions and phosphate ions, each with distinct ratios and structures. These compounds are highly soluble in water and are widely used across multiple fields, including medicine, food production, agriculture, and industrial processes. The most common forms are monopotassium phosphate, dipotassium phosphate, and tripotassium phosphate, each varying in the number of potassium atoms bonded with phosphate units. Despite these structural differences, all forms provide key benefits due to the presence of both potassium, a vital electrolyte, and phosphate, a critical component of cellular energy systems. In biological systems, potassium plays a major role in maintaining fluid balance, nerve conduction, and muscle function. It is one of the primary intracellular cations and is crucial for maintaining the resting membrane potential of cells. Phosphates, on the other hand, are vital for the formation of ATP, the primary energy currency of the cell, as well as nucleic acids and phospholipids, which form the structural basis of DNA, RNA, and cellular membranes. In the medical field, potassium phosphates are commonly used to treat or prevent hypophosphatemia, low phosphate levels in the blood, and hypokalemia, low potassium levels. They are often administered intravenously in clinical settings where electrolyte imbalances are common, such as in critically ill patients or those undergoing chemotherapy or dialysis. Oral formulations are also available, especially for individuals with chronic phosphate depletion. In parenteral nutrition, potassium phosphates are essential ingredients to ensure adequate cellular function and energy metabolism. They must be dosed carefully to avoid complications, particularly in patients with kidney dysfunction, since excess phosphate or potassium can lead to serious conditions like hyperphosphatemia or hyperkalemia. The food industry uses potassium phosphates extensively as food additives, where they serve various purposes, such as buffering agents, emulsifiers, and leavening agents. In processed cheese, they improve texture and meltability. In baked goods, they serve as part of chemical leavening systems. These compounds also regulate pH in carbonated beverages and stabilize proteins in meat processing. The use of potassium phosphates in food is generally recognized as safe by regulatory agencies such as the FDA when used within specified limits. However, concerns have been raised about the widespread use of phosphate additives and their impact on cardiovascular health, especially in populations with compromised renal function. Excessive dietary phosphate may contribute to vascular calcification and secondary hyperparathyroidism, particularly when phosphate intake significantly exceeds what the kidneys can excrete. In agriculture, potassium phosphates are used as fertilizers to deliver essential nutrients to plants. Phosphorus is a major component of DNA, RNA, and ATP, while potassium supports photosynthesis, water regulation, and enzyme activation. Monopotassium phosphate, in particular, is a favored foliar and fertigation fertilizer, meaning it can be sprayed directly onto plant leaves or delivered through irrigation systems. It dissolves readily in water, making it ideal for hydroponics and precision agriculture. Its dual nutrient composition makes it a popular choice for growers seeking to boost crop yields while minimizing environmental runoff. Additionally, potassium phosphates are sometimes used to reduce plant diseases due to their ability to strengthen plant defenses and inhibit fungal growth. In industrial applications, potassium phosphates are employed in detergents, cleaning agents, corrosion inhibitors, and fire extinguishing systems. Their buffering capacity helps maintain stable pH in various formulations. In water treatment, they prevent scale formation and corrosion by sequestering calcium and magnesium ions. They are also used in metal treatment processes and in the formulation of antifreeze and de-icing solutions. In laboratory and biochemical settings, potassium phosphate buffers are widely used due to their ability to maintain stable pH across a range of physiological conditions. These buffers are particularly useful in enzymatic reactions and protein purification protocols, ensuring that the ionic environment remains consistent. Potassium phosphates are generally considered safe when used appropriately, but like all compounds, they must be handled responsibly. In medical contexts, overuse or incorrect dosing can lead to electrolyte disturbances. Hyperkalemia, an elevated potassium level in the blood, can cause muscle weakness, cardiac arrhythmias, and even sudden death. Hyperphosphatemia, or high phosphate levels, is especially dangerous in individuals with chronic kidney disease, as it can lead to calcium phosphate precipitation in tissues, contributing to cardiovascular complications and bone disorders. Therefore, blood levels must be closely monitored during supplementation or intravenous administration. In the environment, potassium phosphate runoff from agricultural use is a concern. While potassium itself poses minimal environmental risk, phosphate contributes to eutrophication in freshwater systems. This process, in which excess nutrients promote rapid algae growth, leads to oxygen depletion, fish kills, and loss of biodiversity. To mitigate this, proper application techniques and timing are essential, as is the use of controlled release formulations and precision agriculture technologies. From a chemical perspective, potassium phosphates are salts of phosphoric acid. They exhibit strong ionic character, high solubility in water, and stability under normal temperature and pressure conditions. These properties make them suitable for a wide array of uses. In laboratory preparation, they are typically synthesized by reacting potassium hydroxide or potassium carbonate with phosphoric acid under controlled conditions. The resulting solution can be dried or crystallized to obtain the desired compound. The specific product, mono, di, or tripotassium phosphate, depends on the stoichiometry of the reactants. The bioavailability of potassium and phosphate from these compounds is high, making them effective for rapid nutrient delivery. In nutritional supplements, they are often combined with other minerals or vitamins to support general health, athletic performance, or recovery from illness. Some formulations also aim to correct acid-base imbalances by serving as alkalinizing agents. For athletes, potassium phosphate may be used to improve oxygen transport and buffer lactic acid buildup, although such claims are still under research and not universally endorsed. In conclusion, potassium phosphates are multifaceted compounds with significant relevance in medicine, agriculture, food production, and industrial processes. They serve as essential sources of potassium and phosphate, both of which are crucial for cellular function, energy metabolism, and physiological stability. Their widespread utility stems from their solubility, buffering capacity, and nutritional value. However, their use must be balanced with health and environmental considerations, especially given the risks associated with overexposure or misuse. Understanding their properties, benefits, and limitations ensures their responsible and effective application across disciplines.